Welcome to problem solving session for the course Linear Algebra. I'm Siddhi Balgambore from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 11. That is problems related to permutations, inversions, and determinants. So let us start with our first problem. It is 15, 8, 17, 4, 7, 14, 18, 13, 10, 6, 11, 5, 3, 12, 1, 9, 2, 16. So this is question. We have to find the inverse of uh, this permutation. So I hope you know what inverse of a permutation means. So inverse of a permutation. So let us recall the definition first. So for sigma belongs to Sn, and inverse of a permutation is a permutation tau in Sn such that sigma compose tau is equal to identity permutation. So let us call it this is identity permutation. That is, everything is mapped to itself. Okay, and we denote this inverse of permutation sigma by sigma inverse. Okay, so it is we need to find one more permutation, sigma inverse, such that when I compose these two permutation, I will get the identity permutation. So that's the question. So there are multiple ways by which we can find this inverse. So first is, let us start with an example, because this permutation is in S18, so which is pretty used to understand in one go. So let us start with doing examples where we are finding the permutations for basic elements. In suppose we are talking about permutation, inverse of a permutation in S3. Okay, so S3, suppose we take this element 1, 2, 3, and this is my permutation 2, 3, 1. So this is again a cycle. So what we do in general is, not in general, I mean, we want a permutation such that it, when I compose it with its that permutation, I get the identity permutation. So it is like, for example, if I reverse these two rows, I will get this. Okay, and if I look at each row now, here 2 goes to 1 and 1 is going to 2. So 1 is now mapped to 2, 3 is going to 3, 2, 2 is going to 3. So 2 is going to, sorry, yeah. We are starting from left, right? So 1, 2, 3. So 2 is going to 1, 1 is going to 2. So 2 is going to 2 again. 1 is going to 3 and 3 is going to 1, so 1 again, and 3 is going to 2, and 2 is going to 3 here. So when we do permutation, we start from the right side and we go towards the left when we do the composition. Okay, it's not commutative. Okay, so we can't start from anywhere, we have to start. So in case of inverse, it happens because inverse is an element such that sigma tau is equal to tau sigma is identity at the end. So it works in this case, but in general, when we are looking for composition of permutation or multiplication of permutation, we start from the right permutation and we go to the and we keep on checking its image in the permutation left to it. Okay, so we start from here and we are going here. So when I switch these two rows, I got this identity, right? So what this means, this is equivalent to, this is just symbol. This is what, if I arrange them as 1, 2, 3, that's how we usually look at the cycles. So it's just 1 going to 3, 2 is going to 1, and 3 is going to 2. So I'm just rearranging this. This is just rearranging these permutation. Okay, so that's what we are doing here. So this is how I got what I say, the inverse of this permutation. So what we do what we do is we can just switch the rows and see what we get and rearrange that permutation. I mean this permutation here, and that is my inverse. Okay, so that's one way. Another way is looking at the cycles. So for example, I got this. So this is cycle, right? So this is cycle 1, 2, 3, and the inverse I got is this cycle 1, 3, 2. So inverse of 1, 2, 3 is 1, 3, 2. Let us check for 4 cycle now. If I take 1, 2, 3, 4 and take this cycle, okay, I'm here taking cycle, but we will also check it for in general permutations. But yeah, so as I said, we will just switch the rows and I will get this 2, 3, 4, 1 is going to 1, 2, 3, 4 here. And this is my permutation. When I compose them, I get new permutation. That is, we will check now. Now here 1 is going to 4 and 4 is going to 1. So 1 again, 2 is going to 1, 1 is going to 2 here again. 3 is going to 2 and 2 is going to 3 here again, and 4 is going to, sorry, yeah, 4 is going to, did I make any mistake? No, right? So 4 is going to 3 and 3 is, yeah, correct. 4 is going to 3 and 3 is going to 4. So 4 again. So yeah, I got the identity permutation, and this permutation here corresponds to this cycle 1, 2, 3, 4. I'm just rearranging them to look to get what exactly we got. So it is 1 going to 4, 2 is going to 1, 3 is going to 2, and 4 is going to 3. If there are any doubt, please let me know. These are just rearrangement, okay? Rearranging this too. So, and if you see the cycle, it was this cycle 1, 2, 3, 4, and here I got this cycle 1, 4, 1, 4, 3, 2. Okay, so in general, if you, and if we can also check for 5 cycle, and you can check that for any cycle of the form A, B, C, D, whatever, uh, or let me take this. If you take any cycle n, its inverse is this 1 and n minus 1 going to 2. Okay, so this is inverse of a cycle in general, and it gives me E again, or identity, or 1 if we want to just denote it. So yes, so this is what we have. And in general, so what we will do is, instead of inverting this all whole, so the essential idea is just inverse the rows and we will get the inverse permutation. But for something like this, where we are given these 18 elements, we can't keep doing that. So the easier way is to convert this permutation into cycle formation, I mean the cycle representation of this permutation, and then use this formula here, this one, and calculate the inverse. Okay, we can try this now. And the cycle of this permutation, cycle representation is, okay, where is it? Yes, so it is one, I'm just copy pasting this here. And I hope you know what cycle representation of permutation is. So 1 is going to 15, and here 15 is going to 1 again. So that's it. This is one permutation. Now the second permutation. Now 2 is going to 8. 8 is now going to 13. 13 is going to 3. 3 is going to 17. 17 is going to 2 back again. So that cycle is done, because now everything will be permitting. For example, now this 17 is going to 2, now 2 is again gone to 8, 13, and the cycle continues. And now next is 3. 3 is done. 4, yeah. So 4 is identity permutation. Sorry, 4 is mapped to 4 itself. Now 5, it's 5 goes to 7. 7 is going to 18. 18 is going to 16. 16 going to 9. 9 goes to 10. 10 goes to 6. Okay. Maybe we'll write this below. 6 goes to 14. 14 goes to 12. 12 is going to 5 again. So now this is new next cycle. And now 10 is there. So 11 and 12 is taken care of. 12, 13 is here. And I think we are done, right? Or anything left? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yeah, we are done. Okay, so this is cycle. And this is also called canonical cycle decomposition. So cycle decomposition, it's cycle decomposition, but canonical cycle decomposition means the least of element is written first here. So for example, this one here, sorry, this one here is smallest among this cycle. This 2 is smallest among this cycle. 5 is smallest. And so these are anyway 4 going to 4, and so one cycle, if you want to call it. So that's not, but yeah, because cycle C, A, B, C, D, it's A going to B going to C, C going to D. I can write this as also like this, right? Because anyway, it is A going to B going to C going to D. So there are many ways to represent single cycle in a permutation. But canonical permutation is when we are arranging each cycle where we are placing the smallest in that cycle, the smallest number in that cycle first, and rest whatever the cycle structure is. And again, we are also rearranging the first terms, this first term in increasing order. For example, I'm not, so here 1 less than 2 less than 4 less than 5 less than 11. Okay, so the first element of each cycle is again arranged in increasing order. Okay, I cannot, so if I remove this 4 from here, and if I place it here, then this is not my canonical representation. Okay, this is another cycle representation for this or cycle representation or cycle decomposition for this sigma, but it is not canonical cycle decomposition. Okay, so for canonical cycle decomposition, we have to arrange the first entry of each cycle to be the least among that cycle, least number among that cycle, and each cycle to be arranged such that the first entry is always greater than the previous entry. Okay, so that's canonical decomposition. So now, yes, this is the inverse. So this is my cycle, and now we have to calculate the inverse of this. So sigma inverse will be what? For 1 and 15, For transposition, its inverse is transposition itself. So for 115, it is similar, the same 115. So I will write this here. So this is my sigma. So 115, 2, 8, 13, 3, 17, 4 as it is. And then 5, 7, 18, 16, 9, 10, 6, 14, 12, and 11. And now I'm just writing its inverse. So sigma inverse will be 115, that inverse of transposition. And now I will use this one. Okay, so it is cycle 1 to up to n. And it is now 1 n minus 1 goes up to 2. So if you want to write this in general form, so the general form for this is, I'm removing this because we don't need it. So in general, if I have this cycle a1 to an, then its inverse is a1 as it is, and an minus 1 up to a2. So this is inverse of the cycle. So for this cycle here, I get 2, then 17, 3, 13, and 8. 4, it's fixed anyway, so as it is. And now again 5, 12, 14, 6, 10, 9, 16, 18, 7, and 11 as it is. So this is inverse. And if you want to check, we can check that right now. For example, 115, so sigma compose sigma inverse will be, now see, 1 going to 15 and 15 going to 1. So product of this, yeah, one more thing I want to tell you is that if I have this sigma, yeah, so how to say this? Yeah, such that, yeah, sigma 1, sigma 2, sigma n, uh, sigma 1, sigma 2, sigma n, be in essence such that sigma k, be in essence such that they are disjoint cycle, they are disjoint permutation. Then we can commute them. Okay. So in general, sigma tau is not equal to tau sigma, right? For any uh, for sigma and tau in Sn. But if sigma and tau in Sn are such that they are disjoint, then sigma tau is tau sigma. Because see, what permutation do, they send they are maps which send some number to another number. Okay, so here if the cycles are disjoint, does not matter how I arrange them. The only thing that would, I mean, what it is doing, for example, I have this two cycles and I'm just writing, this is my tau and this is my sigma. So I'm just writing them as 1, 2. Because ultimately 1 is going to 2, 2 is going to 1. What is happening in particular cycle is not affecting the other cycle. So we can switch, we can permute, we can rearrange them, or we can commute them. Okay. Uh, and yes, that's what I wanted to tell you here. And so when I take product of this, so this sigma compose sigma inverse, I can just look at, I mean, I can just club each cycle, each decomposed cycle to next to each other. And 115, this transposition will give me identity again. And if we check for this one, so we will start with 2 here. So if I arrange them, so it is like 2 is going to 17 here, and then 17 is going to 2. So 2 is going to 2 here. And now we have 8 here. Oh, sorry, 17 here. 17 is going to 3. 3 is going to 17. Now 3. So let me just write this again for you. Let me just show you this cycle here. Or this one. Yeah, we'll take this one and we'll see. So this is what we have. So we'll check so that we don't have to do it for particular cycle. we'll check that this actually give us identity. So A1 is here going to AN, and now AN is going to A1 here, right? This is A1, A2. Here AN now going to AN minus 2 and so on. This is A2. So AN is going to AN minus 1, and AN minus 1 is going to AN. AN minus 1 now here going to AN minus 2, but AN minus 2 here is going to AN minus, yeah, N minus 2 is going to N minus 1 here. Sorry, here it was 1. And so on. And for A2, here A2 is going to A1 and A1 is going to A2. So A2. So everything is now back to its own image, right? So these are so Sn are essentially bijective functions on particular set. And that's what we are doing here. So I hope this is okay to understand that when we multiply them, each cycle will correspondingly multiply with its own inverse cycle, and we will get identity here. Any doubts? This is 17. How the inverse was calculated. I mean, if there is any doubt, please let me know. And we are asked to check for few more things. So for example, for this, we are also asked to compute, so for this above sigma. So let us call this question 2, does not matter. For above sigma, for sigma in what we have compute orbits. I hope you know what orbits is. Yeah, this canonical cycle decomposition, which we already discussed, and signatures, orders of sigma and sigma inverse. And I'll just copy paste this above, it will be easier. And the powers of sigma power, these powers of sigma, that is power sigma power 100 and sigma inverse power 101. Okay, this is what we have to calculate. This is the question which is asked. Uh, yes, so we have to now check orbits. So I hope you know what orbits is. So orbits means where each element is going. So let me just recall what orbit means. So for an element, k in n, or let me write this 1 to n. The set sigma m k such that m in z uh, is called the orbit. Is called the orbit of that element. And note that this orbit, so for example, if I take any, for example, in this sigma, if I take some element, for example, if I take, suppose, say 16. So what are all the images 16 can take when I take powers of sigma? So for example, 16 here, this is my sigma. So 16 is going to 9. Okay, and this is my first cycle, that is sigma. When I take sigma square, so for example, we are taking sigma in S18 as above. And if I take k to be, suppose 16, so 16 here is going to 9. So my orbit of this 16 will be 6. When I take first multiplication, sigma power 0 will be 16 itself. So 16 will be there. Sigma sigma is 16 is going to 9. So for sigma of 16, I have 9. Sigma square of 16 will be, now where this sigma of 16 is going, that is where 9 is going in sigma. That is, it is going to 10. Okay. And every time I do this, we can see that the every power of sigma, when I check it for 16, it will travel only in this cycle, which contains 16 here. Okay, it can never go to any other element. It will stay in this cycle only. I hope that's understandable. If there is any doubt, please let me know. All I'm saying is that this, what is this? This is my sigma 0. See here, we are taking Z. So that does not matter anyway. So it also contains 0. And see, after the, what we say, what if the cycle, if 16 here belongs to some cycle, suppose say sigma k, the cycle. For example, if sigma is my sigma 1, sigma 2, here we have 5 cycles. And 16 belongs to sigma 4 as per our notations. If I call them sigma 1, sigma 2, this is my sigma 3, sigma 4, and sigma 5. So orbit of 6, so 16 belongs to sigma 4. So orbit of 16 is elements of sigma 4. That's what I'm trying to say. Elements of this cycle. It can't take image anything other than elements from this cycle, sigma 4. Okay, if there are any doubt, please let me know. So for each element, the orbit is the elements in the cycle where that original element is belonging. For example, for k, if k belongs to some cycle of Sn for sigma, then all the elements, for example, I hope you understood. There is any doubt, please let me know. Or if there is something difficult to understand, please let me know. I'll re-explain. But yeah, I hope you got the idea, like what I'm trying to say here. For every element, I'll write this statement. I will write this, that the orbit of k in 1 to n in for sigma under sigma is the support, or what the is the set of elements in the cycle in which k belongs under this cycle representation, or what we call it, canonical cycle. I think canonical is the name. Yeah, canonical cycle decomposition. Canonical, or you can just write disjoint cycle representation of sigma. I hope you got the idea. So that's what it takes. It can't take any image other than uh, whatever elements are there in the cycle. Okay, so that is cycle representation. And I hope you know for yeah, next thing. So we saw the orbit. We know what canonical cycle decomposition is. We already did that. We have to now check signatures and order of sigma and sigma inverse. Okay, and yeah, so signature, I hope you know what signature is. So the sign of permutation or signature of permutation sigma is either +1 or +1 if even, or -1 if odd. So it is computed by computed as -1 power k -1, where for each cycle of length k in the cycle decomposition, and then taking product of it, and then multiplying over all the cycles. And we can note this, that for even cycle or even length cycle, signature is -1, that is, it is odd. And for odd length cycle, the signature is +1 and it is called even. So it's actually based on the transposition, the number of transposition we right. For example, for transposition is considered as these transpositions are odd. What I can say, yeah, are odd permutations. Okay, and has sign -1. Okay, so yeah, so essentially this even length, odd length, and this signature of permutation, we say that every cycle can be decomposed as product of transpositions. Okay, and how many transpositions we need in order to write that permutation as a product of transposition is what we see. So any even cycle will need or I mean every even permutation will need even number of transposition, and odd permutation will need odd number of transpositions uh, to write it as product of transposition, and that's where the sign is assigned. So if we need even number of transposition, the transposition becomes even. If we need odd number of transposition, it becomes odd transposition with -1 sign, and so on. So here we have this cycle of length. Here let me write cycle of length 2, here cycle of length 5, this is cycle of length 1, and this is cycle of length 1 2. I think this is 1, so I have 9, so this must be 9 here. Okay, so sigma is cycle, so therefore signature of sigma will be -1 power product of all this, right? So -1 power, first one was 2, 2 -1 power, next was 5, 5 -1, middle one was just 1 -1, the single cycle, the fixed 4, and then it was -1 power 9 -1, and finally again the 11 was fixed, which was -1 power 1 -1. Okay, and this is -1, this is 1, this is again 1, and this is 1, and this is 1. So we are finally getting -1 as a sign of sigma. Is there any doubt here? Okay. So yeah, and similarly, signature of sigma. So note that if we have a particular permutation, um, this is, let me just do this, and I hope you can still see this clearly. Note that here, if I have a permutation here, the corresponding inverse, if I'm just focusing on cycle, if I have cycle of length, suppose k here, its inverse will have same length of cycle. So for example, inverse of a k length won't be some n length where k is not equal to n. Okay, so I'm saying that when I'm looking at permutation, the cycle permutation, its inverse is again a cycle of same length. Okay, for example, you can see this. This is of n length, and its inverse is again is of n length. It's an n length cycle. So when I'm looking at sigma here, each length, when what I'm saying, when I look at inverse of this sigma, I will again have cycles of similar length, exact same length in its inverse. Okay, so signature of sigma and its inverse won't change. They will always be same. Okay, because the cycle structure is what essentially we use to calculate signature. And when we look at the inverse of given permutation, the cycle structure does not change. So the signature of given permutation remains uh, same when we look at its inverse. Okay, I hope that's clear. So here signature of sigma is -1, so it will remain same, and signature of sigma inverse will also be. So similarly, since, let me write this, since the cycle structure remains same, or I can say is preserved when we take the inverse, the signature of sigma and its inverse are same. Okay, and hence signature of this sigma inverse will again be -1. Okay, is there any doubt here? And yeah, and now we have to calculate order of sigma. Okay, order of sigma. So note that in general, if if I write any sigma as product of some sigma n, where this is, suppose, sigma is equal to sigma 1 to sigma k is cycle decomposition or canonical cycle decomposition of sigma, then and suppose length of sigma I is ai, just then order of sigma is LCM of this AI, all these AIs, okay? AK. So this is just fact we know for calculation. Okay, and this is what we will use. We have here sigma is transposition 115, and then 4 is fixed. No, I think there is one cycle of length 5 here, 2 something, and then we have 4 fixed. Then the next cycle, I think it starts from some 5, yeah, 5, and then 11, which is of 9 length. This is permutation, this is 1 length and 1 length again. So LCM of sigma will be, so each of them have order of, let me just write, order of 115 is 2, order of this 5 cycle 2, 8, 13, 3, 17 is 5, order of this, when I'm writing it is cycle, order of 4 is 1, right? Yeah, and order of this 5, 7, okay, 5, 7, 18, 16, 9. I hope this is sigma and not it seems. Yeah, 9, 10, 6, 14, 12. I hope it is correct. And it will be 9 because there are 9 elements, and order of 11 will again be, this fixed 11 will be 1. So order of this sigma will be LCM of all these numbers, okay, 2, 5, 9, and 1. And 1 again. Does not matter, but yeah, let me write it. And it will be 90, right? LCM of this is 90. So order of this sigma is 90. Okay, so what it means that I have to multiply sigma 90 times to get identity permutation. Yeah, and this order here is same as group order here. Okay. This is like the same order as group order of sigma under composition. Okay. So I hope that's clear. And the final thing is we have to calculate, we have to calculate these two things. Yeah, and order of sigma inverse will be again same, okay? And will it be? Yes, it will be. Because again, we are only using the cycle length to calculate the order, and it is preserved when we take sigma inverse. So order of sigma inverse will also be 90. It's not asked, but I'm just mentioning here. And now we have to calculate what is sigma power 100. That is asked. Okay. But note that we are in group. So sigma and 90 is the order. So it is 100, 90 plus 10. Okay. And when I do this, this is sigma power 90 into sigma power 10, right? But sigma power 90 is identity permutation because order of sigma is 90. So it becomes identity. Here, I'm writing this identity. And sigma power 10. Okay, or I hope this is just representation for identity, okay, and nothing else. And sigma power 10. So sigma power 100 is nothing but what I will get when I multiply sigma 10 times, or when I take product of sigma 10 times, or yeah. So let us see how it goes. And again, we know the orbit of cycle is the elements of cycle itself. So when I multiply particular cycle for suppose k times, I just have to take check for this. For example, if I'm looking at this cycle here, the image, when I take powers, the image will be independent of what is happening to other elements. Okay. Whenever I take power, this 2 will be taking image from this elements only, these 5 elements only under this sigma. It won't go to any other element. So it's as good as checking what power of each cycle looks like, and then take product of it. Okay, so what I'm saying is when I want to calculate what is sigma power 10, what I will do is I will check for sigma 1 power 10, sigma 2 power 10, and this all 5 cycles power 10, how they look, and their product is essentially what my sigma power 10 is. Okay, so that's what I'm trying to do here. So what I will do is I will check power of each cycle. So sigma is sigma 1, sigma 2, sigma 3, and sigma 4, sigma 5. Okay. So sigma 1 is my this cycle, this transposition. And then sigma 1 power 10 will be what? This is just transposition, even power. So this 15. So sigma power 10 will be, or we can do this. Sigma 1 is equal, sigma 1 power 10 is 115 power 10. This is 115 power 2 into 5, right? And that is identity permutation 5. So that becomes identity permutation. So the sigma 1 power 10 is just identity permutation. Now sigma 2 is my this 5 cycle. It was it is 217.3. I hope it's correct. No, it's not inverse. 2813.317. 28, right? 2813.317. Yes, and when we take sigma 2, note that order of sigma 2 is 5. Okay, it is odd length 5 cycles. So sigma 2 power 10 will be sigma 2 power, so sigma 2 power 5 power 10. So this is identity 2. So this is identity square, that is identity again. Okay, so sigma 2 10 becomes identity. And now sigma 3 is just 4 fixed. So anyway, it does not change. It will still remain 4. Sigma 4 was my that 9 cycle, which is 5, yeah, 5, 7, 18, 16, 9, 10, 6, 14, and 12. Okay, and I have to look at sigma 4 power 10, but note that order of sigma is 9 because it is 9 length cycle. So it is sigma power 9 plus 1. So sigma 4 9 into sigma 4. So when I do this into its composition in my SN, and this is nothing but identity permutation composed with the sigma 4, that is sigma 4 again. Okay, so sigma 4 remains as it is. And now the final one, sigma 5, is just my 11 fixed, and it's when I take power, nothing changes. Okay, and it just remains as it is, the 11. So we see that this sigma power 100 is actually this sigma 1 power 100, sigma 200, because this, wait, this was, we know, sigma power 10, and that is sigma power 10, sigma 2 power 10, sigma 3 power 10, sigma 4 power 10, and sigma 5 power 10. And that happened because these all were disjoint cycles, and that's why we could we can commute them, and that's how we got this. Okay. In general, if these were not disjoint cycle, we can't do this. Okay, it's happening because the elements we are taking product of a product are commutative, or yeah, yeah, they are commutative. This each cycle is commutative among to the other elements. Okay, that's why we could do this. This does not happen in general. Okay, please understand when we write this here. Yeah, please understand this when we write it here. Okay, it it has some meaning attached to it. If there is any doubt, please let me know. And we just saw that everything was identity permutation except for sigma 4. So in short, this is just sigma 4. So sigma power 10 is just this cycle here. And this we could calculate easily because of two things. We know what order is, so we just got rid of a huge chunk of this power. That is sigma power 100 essentially becomes sigma power 10. And further, we had cycle decomposition. So dealing with each cycle was easy because we know the length of order of each cycle. It's just length of that cycle. And we use that here to calculate sigma power 10 at for each cycle. And then we took the product. Okay, so yeah, so this sigma power 100 is just this 9 cycle. And similarly, sigma power, what we say, sigma power, I think they asked to calculate sigma inverse 101 power. Yeah, this is for sigma inverse. So, okay, we are taking too much of time, but yeah, we can't help it. Uh, so sigma inverse power, I mean, you have to do the similar thing, okay? We have cycle representation of sigma inverse here, and I hope you can do. We will move to next question now because it's taking, yeah, we have sigma inverse here. Just do what we did to sigma, same thing, and we will get sigma power 101. So sigma inverse power 101. Again, check the permutation. There, all the cycles will survive because it's like we are taking one extra thing because sigma 1, sigma 5, sigma 2. So it will be, let me just write this quickly. Sigma inverse power 101 will be sigma inverse power 90 plus 11. Okay, and this will be sigma inverse power 11 essentially. And but for each, because of odd cycle representation, we know this will be sigma 1. And for example, if this is my sigma 1 inverse, sigma 2 inverse, sigma 3 inverse, sigma 4 inverse, and sigma 5 inverse. We know this, and each power 11. And we know order of first one is 2, so this will be sigma 1 inverse. This here again we know order was 5, so again this will survive. One power will survive, so this will be sigma 2 inverse. Sigma 3 was just 4 fixed, so the 4 fixed will remain as it is, and essentially, and here it was 9, so it is sigma 4 inverse square. Okay, and here again this was fixed 11, so this will remain as it is. So this is essentially what we will get. Here we all these sigma 1, sigma 2 vanished, only sigma 4 survived. Here everything is surviving along with some extra terms. Is that okay? I hope, I mean, now you just have to plug in what inverses are. You just have to, we know what expression of sigma 4 inverse is. Just plug it in here. So we'll move to next question. Yes, it is. Question 2, let x and y be finite sets with order this cardinality of x and y mn, and they are letting, suppose sigma belong to Sx and tau belong to Sy, and we have to compute the signature of following permutations. We'll quickly do this. So this is my permutation. Xy is going to Yx of Xy. Okay, and second is this sigma. This is called disjoint union. This sigma and tau belongs to this S of X disjoint union Y, defined by sigma, this disjoint union tau, restricted to sigma is just sigma. Sorry, restricted to X is sigma. Tau. And final is this one, sigma cross tau in S xy, defined by, yeah, this is just, okay, so this is what is given to us, and we have to calculate signature of each permutation. So I hope you understand what permutation here are. First of all, when they are writing this, so I will explain each as we go further. So first one, this is my permutation. When they are writing this, what does this mean? So this is xy going to yx, and everything is happening in x cross y, right? So this is permutation in x cross y, s x cross y. Okay, so when they are doing this xy going to yx, understand that this x and y here must have same size, otherwise it won't make sense. Okay, so what I'm saying is, if I'm looking at, suppose my x is this 1 2 3, and my y is a b, suppose, then when I'm writing this again needs to be an element of x and y, x cross y. Okay, so for this to make sense, that x and y must be same. Okay, so for this x comma y going to yx to make sense, note that x must be equal to y, otherwise it won't make any sense. X must be equal to y, or you are looking at just cycles, so in that sense x and y must have same size at least. So when I'm saying this, I mean, does not matter how you are representing your what I can say, this permutation. For example, if you're doing it on n numbers, for example 1 to n, or n variables, say 1 to n, does not matter, as long as their size is same, we can make sense of what that permutation look like. Okay, uh, yes, so we have this information with us that x and y are similar here, and this is what it is. So for what it means is, for example, if I'm taking this, my x is just these two elements 1 2, so I'm looking at s2 in essentially, or let me take one more 3. So what it does is, if I take sigma is equal to 1 2 3 and tau is equal to just 1 2, so when I do this, 3 is fixed. This sigma cross tau, right? That's how they have represented it. Yeah, that's what it means. Not cross. Yeah, I mean this sigma tau is now going to tau sigma. So element here. So 1, 2, 3, comma 1, 2 is going to 1, 2, comma 1, 2, 3. That's what it means. Okay, and we have to now calculate permutation, uh, signature of this permutation. So yeah, is this okay how it looks like? And then we have to calculate. So essentially we have this sigma going from xy to yx on x cross x with cardinality of x as m. So suppose x is 1 to m. So this x cross x has size m square, right? So we have to find the cycle decomposition of this sigma here. And note that there, uh, the diagonal entries are all 1, 1, 2, 2, 3, 3, and so on. So there, for first, for diagonal entry, mm, yes, this sigma of 1, 1 will go to, or sigma of I will be just I. So these are fixed. Okay. And for second, for non-diagonal or off-diagonal with I not equal to j, this sigma of ij will be ji, right? And sigma of ji will be sigma of ij. Sorry, just ij. I hope you understand what we are doing here. So this will give me, so this forms a two cycle, ij and ji. And number of such two cycles is all the unordered pairs. Yeah. I comma j with I less than j. Okay, so and so it is, and which we know, so that is So we have to just calculate all the possible pairs of ij with I less than j. So and that we know is m choose 2 since there are m symbols. Okay, so each 2 cycle has a length 2. So for these 2 cycles, after of these 2 cycles here is, so signature will be minus 1 power 2. So 2 minus 1, that is 1. And for each diagonal entry, that is one cycle that was diagonal entry, has length 1. So that will be just, so sign will be minus 1 power 1 minus 1. That will just be 1. Okay. So collectively the total sign is, let me just check this. Yeah, so the only thing that contributes to cycle is this odd part. Sorry, this 2 cycle part. And oops, that was, so this will give me, yeah, this was minus 1 and this was plus 1. And each such, there are m choose 2 such cycles, and here anyway cycles are positive. So in short, uh order of each order, or what I was saying, yeah, total signature will be this plus 1 power m, because there are m entries in diagonal, into this minus 1 power, since for each such transposition there are m choose 2 possibilities. I have this, and essentially I have this as signature of this permutation, sigma. Total signature of sigma is this. Okay, yeah, and I hope that's okay. So what it was, so we are looking at x cross x, and x cross x was going to somewhere. Okay, so for example, what we were doing is, for example, suppose my x is 1, 2, 3. Okay, so we are talking about permutations on x cross x. So permutations on x cross x. That is what we have to. So what will x cross x will be? It will be this 1, 2, 3, 1, 2, 3. Sorry, how it look like? So it will be some kind of, I mean, it will be a grid. Okay. And it will be 3 cross 3 grid. And there, whatever here was, they are switching to the opposite diagonal thing. So the permutation sigma is such that if I have this ABCD, so it is just switching this. A is going to A, F is going to F here, and J is going to J. So this I entry which we were talking about, it remains as it is. And only thing was this was switching. So it became B. I mean, I'm just trying to make sense out of this. I mean, I'm just trying to explain it like this. And now I have to find signature of this. Like, how many compositions we need to obtain this. So here this is -1 so not m by 2, it is m choose 2. So such compositions, how many I need to do in order to get uh what we say, my original identity composition. I mean everything filled with 111 and so on. Okay, so please try to understand. If there is any doubt, please let me know. Are there any doubts here?
That seems to be okay.
Yes, so see, elements here are of this kind, right? 1, 2, 1, 3. It's Cartesian product. We know how elements there look like 1, 2, 1, 3. Uh, there will be 9 such, right? And or
2 1 2 3.
6, yeah, 2, 1, 2, 3, 2, 2, yeah, 1, 1, 2, 2, 2, 3. Those will be also there. 3, 1, 3, 2. Or did I make mistake by taking both the similar? But does not matter. And 1, 1, 2, 2, 3, 3 are there. And the permutation is that xy is going to yx. That's my permutation here. So this is my x cross x, and my permutation is this now. If I arrange them like this, 1, 2, 1, 3, 1, okay, 1, 1, 1, 2, 1, 3, and so on, like this. So it is this permutation now. 1, 1, because x going to itself. Now this was my 1, 2 entry is going to 2, 1 entry, and so on, like this. Okay, and I again have this similar structure. Since we are doing this 1 to 2, 1, uh, it looks like just take square and we will get it back. But that's not what is happening here actually. It there is more to it. If I take, instead of 1 to 3, if I do ABCD here, if I take 1, 2, 3 and take it with ABCD here, I mean it will take, we are just calculating signature of it, right? So yeah, I mean just cycle representation of it. So one, I don't know, just try to do this and you will get the idea with different symbols, because here it looks like everything is going to same thing, but that's not the case. Okay. Uh, is it okay? Let me. So this was my sigma here to start with. Yeah, so let us move to second one. Second is just disjoint union here. Okay, so disjoint union means we can completely take different elements and nothing is actually affecting the other one. So whatever signature we have here, so second one is just having, I mean, second one is disjoint union, right? We are taking the sigma and tau in S of X disjoint union Y. So they are essentially different cycles. They are not interacting with each other at all. And it will just be product, like product of, so what I'm saying is, uh, this signature of this, not this sigma direct U, this will be just product like we have for disjoint cycles, because this is literally disjoint union. Nothing is interacting with each other, unlike this one. here elements here and here, it's different, okay? So here it will just signature of sigma into signature of tau. Okay, and because they are disjoint cycle, just disjoint union of this x and y. So it is essentially what we are saying, imitating what happens in disjoint cycles. We just take product and yes, but is that I mean, any doubts here? Yeah, so this one, yeah, let me just do this. So we have to find, this was my sigma, right? And here this 3 1 will go to 1 3. So everything is like this 1 1 is fixed. This 1 2 and this 2 1 will give me another cycle. And the all those disjoint cycles. And this will end here. Yeah, such two cycles I'm getting, right? This 1 1 2 2 will as it is, and these are the transpositions we are getting. And there are m choose to such, because see, once I have 1 3 here, 3 1 is gone again. So there are m choose 2 choices. So that's why the signature was -1 power m choose 2 there. I hope now it's easy to understand when we express it as transpositions. The first one. Second one is pretty trivial because we are looking at disjoint cycles. For example, if I take sigma to be x to be 1 to 10, for example, and y to be 11 to suppose 50, does not matter, or suppose take a to z. And signature of this is disjoint union. So how to say this? The number of transpositions will just be product, right? Because see, we are trying to write them as a cycles essentially. And what I am saying is, since they are disjoint, nothing will change here. For example, here 1 2 was going to 2 1 was still making some sense. Okay, because both the sets were same. Here they are disjoint, so there is nothing of the sort 1 2 is going to 2 1 or anything like that. They are completely disjoint, so no interaction with each other. So the number of such transpositions will basically depend on each independent set. So signature is just product like we do for disjoint cycles, okay? Or A1 to AK. If there is any doubt, please let me know, okay? I'll try to explain as much. Okay, so this disjoint union actually means we are looking at each element as, I mean, we are just taking this as a set now, and A1 to AK. And now we are taking any sigma and tau here. So this sigma will be here and this tau will be some S element from this Y. So essentially it is sigma 1 coming from this M elements and tau coming from this K elements. And so whatever signature of sigma here, whatever transpositions we are writing, sigma 1 to sigma K, for example, no, K, no. Suppose take P and tau will be tau 1 to some tau R. And so individual, what I'm gonna say, individual signature is still preserved. That's what I'm trying to say here. So disjoint union is just we are taking them, looking at them as one set whole, where this 1 to M are not interacting with, does not belong to orbit of AI to AK. So they are essentially disjoint cycles in this disjoint union, and so signature is preserved. So any doubts? Look at it like S of this set, S of this set. And you will understand that whatever is happening for sigma, there will be some signature of sigma, there will be some signature of this tau, and it will essentially be product of these two. Okay, and the final one is again on x cross y. Now the x and y are different, and permutation is, what is the permutation? Yeah. Now it is again sigma cross tau in S x cross y, and yeah, such that sigma cross tau of this xy is going to sigma of x comma tau of y. This is what is given to us. Okay. So the elements of x cross y are again, if x has cardinality m and y as n given. So this is permutation on this m into n, mn elements. And this permutation is such that each element of this grid is going to sigma x and tau y. And now we have to find the signature of this. And we will understand this one. So to compute signature of this sigma cross tau, this we consider this permutation matrices. Okay. Okay, I hope you know what permutation matrix is. So for example, if I take sigma in Sn and for example, sigma of I is some j, then this, how to write this? Sigma of, yeah, I is essentially sigma j, for example, where this sigma I. I hope you know what sigma means. So what it does is we start with identity permutation, identity matrix, and if of n cross n, this is of size n, and if sigma of I is going to j, then here I do the same. So sigma 1, if it is going to, or let me write this one explicitly, of 3 cross 3. Suppose sigma is equal to 132 in Sn, S3. Then what permutation matrix is? Permutation matrix of sigma, permutation matrix of sigma is the columns I will look at. So the first column of my identity matrix will go to third column here because 1 is going to 3. So the first column here will start with identity matrix 1 0 0 0 1 0 0 0 1. And now this 1 is going to 3. So my first column becomes third column, which is 0 0 1. And now second column is going to first one. So 2 is going to 1. So my second column becomes 1 0 0. And the third one, my 3 is going to 2. So third columns becomes my second column of identity matrix. And this is permutation matrix of sigma. And determinant of this matrix is actually determinant of this permutation matrix. It is, if we denote it as P sigma, is actually signature of this sigma. Okay, this is what is known. Okay, so we will use that. We will use this permutation matrix to find signature of this permutation here. Okay, and then we see that the permutation matrix of this one, this, if what to call this one, if I call this row, for example, this permutation matrix of row is the Kronecker product of this P sigma and P tau. And I hope you know what chronic product of two matrices is. So if A is a matrix Aij and B is a matrix Bij, so chronic product, it is denoted by this. It is of this. It is A11 this B, A22 B, so on. Sorry, not 22. A12 B, and am I correct? Yeah. A1 and B, and so on. A21 B. So it is essentially what we are doing is A11, B1. Each of them are now matrix. Each entry is now matrix when I'm looking at it here. And it is A11, B1, A11, B12, A11, B13, so on, A11, B1, and so on. And similarly, the column, it will be A11. So it is entire matrix A11, B1, N, oh sorry, N1, and A11, B, and N. And here, next row starts with A12, A12 again, B11, and so on. So this becomes now n square cross n square matrix. Here we have m or n, does not matter. It becomes m square cross m square matrix. And product, a determinant of this matrix is determinant of this is actually a determinant of, and this can be done for, wait, can this be? No. Yeah, so determinant of this matrix is determinant of A power this dimension of B into determinant of B power dimension of A. Okay, and here we know that dimension of X is M, dimension of Y is N. So therefore determinant of this sigma and tau, sorry, determinant of this p sigma cross p tau will be determinant of p sigma, that is signature of sigma, power p tau. Dimension there is n, for y it is n, and here the signature is of tau, and dimension of x is m. So this is what we get. Signature of one element, power of the another set. That's what it is. And that is nothing but signature of the sigma cross tau. Is there any problem? I hope you understood what this means here, okay? So for example, if I have set, let me just, yeah, if I have this kind of set, second one, and just a second. So for example, if I take set like this, 1, 2, 3, and my y is a b, suppose. Okay, so my this sigma cross this x cross y is this 1a, 1b, 2a, 2b, 3a, 3b. Okay, this is my x cross y. And if I take sigma here, suppose sigma is equal to 1, 2, 3, and or let me take 1, 3 just, and tau is just two elements, so only AB will be there. So this sigma cross tau, this permutation is essentially, I will arrange all this 1A, and here 1A will going where? 1A will go to where sigma is going. That is sigma of 1 is going to 3 and A is going to be here. 1B, for 1B it is again 3 and B is going to A. Second, now 2A, for 2 is fixed, so it will go to 2. A is going to be here. And now 2 as it is, 2 is going to 2. 2B is going to 2A. And now let me just, so now 3A, 3 is going to 1B and 3B is going to 1A. Okay, this is my permutation is sigma cross tau. Okay, and now I have to check the signature of this one. So what we do, we know how signatures are calculated, right? So here, just because these are transpositions, going to transpositions, everything will be 2 cycles. This is anyway, yeah. So these are all 2 cycles here. 1A going, this is 1A, 3B, 3B going to 1A. So we will get such 3 cycles for 2A, 2B. And again for this one, so I will just color them same. And this will go to this and this. So these will be 3 transpositions and signature will be power 3. So it will be 2. And anyway, signature here of each one was -1, -1. And I got, so essentially I get signature as -1 here. Dimension here of first one, it becomes -1 power 2. For second one, it becomes -1 power 3. And again, I get -1 as a sign. So from both, I hope you understood that the formula which we got here actually makes sense and is correct and follows from the example as well. Okay, so I hope you understood what we are doing here. Okay, so that's it. So this is how the signatures are calculated. We just have to check the transposition. So all we are doing is trying to find the transpositions, corresponding transpositions. And for this one, please, we just went to this chronic product, but how it comes, please try to do it with examples, then you will get the idea. Okay, and go to next question now. We'll just do one. And I mean, there are few, I will write the question entirely and we'll do only for couple of them. Yeah, which of the following maps f from r square cross r square to r are bilinear and symmetric? Okay, so we have to check whether they are bilinear and whether they are symmetric or alternating or respectively alternating. So I'll just recall the definition of all three. First, let me write the question. F of x1 comma x2 y1 comma y2 is going to x1 plus y2. B is f of x1 comma x2 y1 comma y2 going to x1 y2. Let me write it easy. C1 is f x1 comma x2 comma y1 comma y2 going to x1 x2 minus y1 y2. D is, I'm not writing again, it is x1 y2 minus y1 x2. And fifth one is, sorry, x1 y2 plus y1 x2. And we have to check whether it is bilinear, symmetric, and all other properties. So what bilinear means? Just copy paste this. Okay, and bilinear means, I hope you remember everything, that f is, if it is from W to R, here our V and W are R2. Okay, and such that for all A, B in R. So when I'm writing this, I'm assuming this V and W are vector spaces over R. So AB is from R, and the vectors, my UU dash are from V and VV dash are from W. So it must satisfy two properties, that f of AU plus BU dash comma V is AF of U V plus B F of U dash V. And second is f of U comma A plus B, okay, AB plus BV dash is A F of U V plus B F of U comma V dash. Okay, so these are the two properties it must satisfy. Okay, and since we are over R, it's not a problem, but if we are doing with complex numbers, we have to take conjugates common and everything. But okay, we are in R, let us focus on that. And the symmetric property is that for symmetric, we must have this thing, first of all, that both the vector spaces must be same. And the property it must satisfy is f of uv must be is equal to f of vu. And for alternating, f of it is again from same vector space. Product, Cartesian product is of two same vector spaces, and it is f of uv is minus of f of vu. Okay, so kind of skew symmetric thing. And in here, f of u must be 0, the way f is defined. Okay, so these two resemble the matrix properties. If you see the symmetric matrix and skew symmetric matrix. So this resembles symmetric matrix and this resembles skew symmetric matrix. But yeah, we have to check now whether given functions will do for 2 and 2, 3 among those. So first one, that x, I will be writing bold x and bold y for this x1, y1. Okay. So first property, bilinear. So first one, we have to check these two properties, that f of this thing, let me write, yeah, f of ax1 plus bx2 comma y1. I have to check whether it satisfies. So this is will be what? X1 as it is. So, oopsie, am I correct? See, we have to take now two elements, right? Because f of x1, x2 plus, okay, we must have three elements first of all. U, X, how? Yeah, yeah, that's okay. So we will take this two. Let me write this properly. A x1 comma a x2 plus b x1 dash comma b x2 dash, right? Comma this y1 comma y2. And now this will be equal to first coordinate. So this is f of this a x1 plus b x dash x1 dash comma ax2 plus bx2 dash comma y1 comma y2. This is my element. Now I will apply f on it. So the first entry and the second entry. So this will be ax1 plus bx1 dash plus y2, right? X1 and y2. So this is my x1 here. Now this new x1 and new x2, and this is my y1, y2. So my map is x1, y2. So this as it is. And this will be equal to my f of ax1. I mean, if I calculate them separately, I will still, wait. So will I get the same thing? Because see, f of ax1 comma a, sorry, I want this to be equal to af of uv and bf u dash v. But the moment I do that, see this, f a into, right? So a into f of x1, x2, comma y1, y2 plus b into f of x1 dash, x2 dash, comma y1, y2. So this is a into f of x1, that is x1 plus y1, sorry, y2. And here this is b into x1 dash plus y2. So this is something different, right? ax1 plus bx1 dash, that is okay. But along with that, I'm also getting here ay1, ay2 plus by2. So a plus by2, which is not what we got here. Okay, so that's why this is not what we want. Okay, so this is not a bilinear map. And the moment we do not have it to be bilinear map, we can't talk about it being symmetric and everything. Okay, so these properties symmetric and alternating properties are properties of bilinear map. Okay, so if something is not bilinear, we can't talk about it being symmetric or alternating map. So yes, the first one was not symmetric. Second one, second one is this x1, x2, y1, y2 going to x1, y2. And we have to now check again the same properties. This f of x1a, x1 comma x2 plus b x1 dash comma x2 dash comma y1, y2. And it will be f of ax1 plus b x1 dash comma x2 ax2 plus b x2 dash comma y1, y2. Okay. And x1 into y2. So x1 is this a x1 plus b x1 dash product. I'm multiplying it with y2. Right? So yeah, so this is my ax1 y2 plus b x1 dash y2. This is what I got. And separately, the left hand side is this ax1 x2 comma y1 y2 plus I wanted b x1 dash x2 dash. Sorry, here this is a here outside. A x1 x2 y1 y2 plus b f of x1 x2 x1 dash x2 dash comma y1 y2. And this becomes now a x1 y2 plus b x1 dash y2. And this is exactly what we have. And we can also check it for the in the second coordinate. And it will be a bilinear map. And for symmetry, we have to check whether we switch, then we get symmetric or not. So yeah, so what we have to check whether f of x1, x2. So yes, binary, bilinear map. And to check symmetry, whether f of x1, x2, comma y1, y2, whether it is equal to f of y1, y2, comma x1, x2 or not. But what is this? F of x1, x. So I'll just write this here. This is equal to x1, y2, and this is equal to y1, x2, and they are definitely not equal. Okay, so it is not symmetric. So not symmetric. Okay, for alternating, what we want is this thing to be minus, right? I want this to be minus of this thing. But what is here? This is my x1, y2, and this is my minus y1, x2. And again, these two are not equal, so not alternating. Okay, so I hope this was fine. And now the third one. Third one, if you go and check, third one will again be non-bilinear. I want to check one with. This won't be bilinear. Okay, you can check. Not bilinear. 4. Fourth one will be bilinear, okay? Because see here, the first one, it will be ax1 x2 square. So it will be uh, a square x1 x2 in first for example left hand side of this one. What I'm saying is that here when I'm calculating this will be a1 square, and it will be a square something, and v will be as it is. So but on the left hand side here it will be a x1 x2. So here I will have x1 square, sorry, a square x1 x2, but here I will only have a x1 x2. I mean, just observe this statement here. Okay, and you will understand that it won't be the case. And similarly for here, uh, it will be bilinear, because one a will be contributed from here and the other one will be contributed from the y2 here, which will be b. So it will be ab and ab. So this will hold, and this will also be bilinear. And you can check for symmetry and alternating map for this one as well. I mean, I hope that's okay. I do not want to spend much time on that. We'll quickly go to this next question related to inversions, because yeah, I think it is question 4. So for the following permutations, compute the number of inversions. I will recall what inversions is. Inversion and the signature. We won't discuss much about signature for this one because we already discussed enough of signatures. The following permutations. There are many. You can go through assignment sheet and we'll just discuss 2 of those. First one is I going to n minus I plus 1. And okay, so inversion, the definition is that for a permutation, sigma belong to Sn, and inversion is an ordered pair of indices I, comma j, such that when I take I less than j, but this sigma I is greater than sigma j. Okay, so inversion is, so for example, for pair I less than j, I have to check whether sigma I is greater than sigma j or not. And when I do this, I have this ordered pair. Okay, here this pair. This is my ordered pair. I comma j, I'm talking about I being less than j. And I want it to be such that this sigma I is greater than sigma j. So it is like for each I less than j, I'm checking whether sigma I is greater than sigma j or not. So for example, if A is less than B, then the image of this I mean A which was less than B under this sigma, whether this is inverting or not. That's what I'm checking. So it's like I'm checking whether my how disordered or how out of order my sigma is. So I'm checking for a less than b, whether sigma a is less than sigma b or not. That's what I'm trying to check. And whenever that's not the case, I'm calling it inversion. So it's like I'm inverting something. It's for that pair. Okay, so uh, that's what inversion is. And also and so this collection and the number of inversions uh, is denoted by this z of sigma, and it is the total number of just the number of the total number of inversions in sigma. Okay, and that's it. I mean, I hope you understand that. So for example, if I have sigma is equal to 3142, this is my cycle. Okay, then for each pair I will check. So for example, if I take only if I write 424142 3. So here for each pair 1 2, if I take 1 and 2, 1 comma 2 is going to what? 1 is going to 4, 2 is going to 3. Okay, corresponding sigma of this pair. Okay, so this is not permutation now. This is pair ij. Or let me just do this. This corresponding 1 2 is going to 4 3. So 1 2 will go to my inversion. Similarly, if I take 1 3, for example, 1 comma 3. So here 1 is going to 4 and 3 is going to 1, right? So this is again not inversion. So but let me take 2 and 4 here. So 2 is to 1. Yeah, let us check for ours. 2 is going to 3 here and 4 is going to 2. So again not. So do we have any pair for which this happens? For example, 3 is going to 1. Yeah, so if I take 3 and 4 now. So 3 is going to 1 and 4 is going to 2. So here I is less than. So, so this is not inversion. All these were inversions. Okay. Because pair was switching the order and so on. Okay. And we also have connection that signature of sigma is also minus 1 power this z of sigma. Okay, so there are many ways to define signature. So one is terms of inversion, the another is determinant of permutation matrix, which we defined, and also the using the cycles and transport. Using the cycles also we can do this because we know if cycle is odd and even. And the another way to calculate signature is again representing the given permutation as a product of transpositions, and the number of transpositions which we get there. Power minus 1 power number of transpositions is what my sigma is again. Okay, so there are many ways signature can be defined. And yeah, for some examples, one is used, for others, it's easier to look at whatever you feel convenient, you can do that. Okay, so for I less than j, So first one is this permutation sigma is such that my I is going to n minus I plus 1. So my sigma is such that sigma of I is going to n minus I plus 1, right? This is what my sigma is. So for I less than j, note that for I less than j, this will imply that minus I is greater than minus j, right? So this will imply that n minus I plus 1 will be greater than n minus I plus 1. So this will imply that sigma of I will be greater than sigma of j. Just basic calculation. So yeah, so each pair I less than, hence each pair I less than j will give us an inversion, right? So, and how many of such are possible, I less than j? Since we are in Sn and we know that there are n choose two possibilities of I less than j or I comma j in n. Okay, this symbol I hope you know. This is just this, okay? Shorthand for the set 1 to n. Okay, so z of sigma hence is n choose 2. And you can do this for other examples also. One more thing, since we also have to discuss determinants, I will just quickly, one of the questions in assignment is discussing the proof of Cramer's rule. Cramer's rule for non-homogeneous system, or we can also use that for homogeneous, but does not matter. Yeah. Proof of Cramer's rule. So I won't be writing everything explicitly, but yes. So the question is proof of prove the Cramer's rule. And I just want to. So what is Cramer's rule? If my epsilon b is a11 x1, a1 and xn is equal to b1, so on a1 no an1 x1 a n n xn going to be n, then if determinant of this aij is non-zero, okay, so if eb is ax is equal to b and determinant of a is non-zero, then each xi is determinant of this matrix or xj. A1 1 going to a 1 j minus 1, a n 1 going to a n j minus 1, and instead of the jth column I'll switch it by b, the b column, and again I get this I 1 j plus 1, a1 j plus 1, so on a n j plus 1, so on, and again n 1 n a n n divided by determinant of this A matrix. Okay, this is my, so because we are dividing it by A, we need determinant of A to be non-zero. And how the proof follows is, remember when we discussed this system of linear equations, I told you already that if I have AX is equal to B with A invertible, or non-singular, invertible, then this X will be A inverse B. It will have unique solution and it will be A inverse B. Okay. And so the idea is similar. And we know how A inverse is calculated using adjoint matrix and so on. Okay. So the proof is essentially the same. So formula for A inverse. So formula for A inverse is this 1 by determinant of A into adjoint of A, right? And adjoint of A is collection of all minors of A. So I hope you know what adjoint of A is. Okay, it is cofactor matrix. So for example, the this is again a matrix where ijth entry is determinant after removing the ijth entry, I column, ith row and jth column. That's adjoint matrix. Okay, and let me write. So ji entry of adjoint of A is the cofactor Cji of A, that is minus 1 power j plus I, determinant of Mji. Okay, and Mji, where Mji is the matrix obtained by deleting jth row and ith column. Okay, so that is my adjoint matrix. So essentially, when I write this, so when I have this X is equal to A inverse B, A inverse is what? It is, so for each Xi will be A inverse Bi, right? So if I want to write this, X is what? A inverse B1 Bn, right? This is X1 to Xn. So this is A inverse. Each entry will be this. How to how to how to explain this? I mean, we have to take A inverse and add it, right? I mean, that's how we will get. Uh, what I'm trying to say is each this xi will be um summation j from 1 to n A inverse ij bj. That's what it will be. Okay, you can check this because if I have this, suppose not b, suppose take c11, c1n, cn1, cnn, and if I take b1 to bn, what this is whatever the first row and column, second row and column. So xi is first row and column. Okay, so xi is, I'm taking the ith row and the column b1 to bj as it is. And what is each ijth entry of this bij? It is 1 by determinant of A. Using this, we have hold of each entry of A inverse because of adjoint matrix. So it is 1 by determinant of A, bj as it is, and each entry is just summation j from 1 to n, cji of A, okay, cofactor of A into bj. And if you do the expansion, I mean, what we are trying to do is we are trying to say that this xij will be exactly this. So we anyway got hold of this denominator here, and so the numerator that is that is determinant of this matrix. We have to check this one actually, that b1 to bn, and how it looks like. So determinant of this AI is this AI. So let AI denote the matrix A replaced by ith column by B. And this determinant of AI will be what? If you check, it will be summation j from 1 to n bj. I mean, it is like we are evaluating that evaluating the determinant using that ith column, which contains the entry b1 to bj. Okay, and this will be again minus 1 power j plus I determinant of mji a. This is after reducing those two columns. And that is nothing but, this is nothing but cofactor, right? This is cji of a, and that's what we have here. And that's why a becomes this divided by determinant of a. Okay, so this determinant of ai is essentially this determinant of a inverse bj. So therefore xi becomes determinant of ai by determinant of a. Okay, this is what, so what we did was xi directly from the, xi directly from the formula is this. And this here, what we have here, we showed that it is nothing but determinant of this matrix ai where I column is replaced by bj. Okay, and that's what we got. That's how we get that xi is essentially determinant of those column replaced matrix divided by a. Okay, so I hope that's okay. I mean, it's fine. If there are any doubts, please let me know. Or we can stop now. Is this okay? Okay, if there are no doubts, then we'll meet next week. Thank you.
Thank you.
Sure.